Hi my friends, today we'll study this interesting mechanism, what governor, which I posted on GrabCAD in 2016. You can download the assembly and all the parts from GrabCAD by using the procedure in my tutorial Inventor number 187. We'll create a dynamic simulation and we'll see how it is the behavior of this mechanism. When you rotate this central subassembly, the balls will move up and the sabots, these are sabots, will come in contact with the drum. This is the drum, and the rotation will be slowed down. The Watt governor was invented in 1788 by James Watt. Now watch the movie. At first the balls fall down due to gravity, then the central subassembly begins to rotate and, as you can see, produces the contact of the sabots with the drum. This contact will stabilize the speed of rotation. This is the assembly. The movement comes from this gear and rotate all the central subassembly. We can see all the details here, and if you want you can click on some part and apply Alt T for transparency, and now you see that there is a key inside, for instance, and also a key up. Yes, I will make them visible back, and I want to mention for you that I don't intend to create the assembly for this mechanism. You have all the components at your disposition and you can create this assembly without problems. We'll focus on the dynamic simulation and details about what happens when we change some things in this assembly. Okay, take your time to create the assembly for yourself. Okay, this is the assembly downloaded from GrabCAD, and my only intervention was to apply view, two lights and settings, just as I did in the previous tutorials. I don't make it again here. Yes? Good. We start by applying dynamic simulation. All the data are here in the assembly. I don't edit anything, I don't change anything, because I want to start together with you. You see, I have here a message about the lights, which are different from Inventor 2014, which was used to create the assembly, different from today. This is why I change the view. Okay. The first thing I do is to unsuppress these four contact joints because they were applied at the end of the simulation for you to see what happens when we don't apply contact here between the sabots and the drum, but here between the mobile hub, this is the mobile hub, and the fixed hub. If you eliminate the sabots, the rotation permits the contact between these two hubs. So I want to start with sabot contacts, not hub contacts. This is why I unsuppress joints here. Now they are visible like the others. I also change the number of images per second. Instead of 5,000, I place 500 because we don't want to have such a long time of functioning. However, this will create the possibility of stopping because of the processor. When you reduce the number of frames per second, the speed of their succession increases, no? Causing the processor to overload and hang. Let's see. Start. First is, as I said, the gravity action, and now impossible to solve the system. Check the definition, blah blah blah. This means that the processor was overloaded. Okay, I go back, I select the construction mode, and I'll leave here 5,000. Yes, take a look with the take a look carefully and see what happens at the beginning. These are getting down due to gravity, and then the rotation starts and the balls are moving up. Look here, now is a slow motion. Now starts the rotation. All the data are collected. Look to the start of movement. Here is the trajectory of one ball. You see? And that trajectory is like a helicoil at the beginning. Then some contacts are repeated here, yes. Sabots and the drum are in a bouncing mode. And it comes the stabilization of the rotation. Now the rotation is stable. You see? If I activate the output grapher, we see the behavior and the speed. Yes, this curves not as we expect to be, can be corrected, and I'll tell you what is the procedure. I changed some things to see where is the cursor. I think that's enough, because now it is stabilized. Stop. Wait a little to collect all the data. You see, not responding. The processor needs to collect the data. We have to wait. Don't worry, this is normal. I have a good computer and it works hard. I go at the beginning, I change to the construction mode, and I'll change the time from 5 seconds to 2.5 seconds here. Yes? And now let's change the presentation of the graph. As I said, right click on the graph and select Grapher options. Yes, various table, and I uncheck this predefined format. Yes. Okay. Now when I start the rotation again, we'll see the normal graph. You see, real curves. This is the bouncing of the balls due to gravity, many bounces, and then starts the rotation. When? At the 0.5 seconds. You see? The rotation. It is very interesting. I was amazed what Inventor can do in more complex situations. It can offer you a very good accuracy and a very suggestive presentation of what happens to the dynamics of the mechanisms when they are in moving state. You see, the bouncing is in between the sabots and the drum now. Till they are in contact, I want to tell you that the friction coefficient is 0.2, created by me. Yes, imposed by me. And I'll show you immediately this thing. Because of changing the time from 5 seconds to 2.5 seconds, the dynamic simulation module needs to collect data again. That's all. Now again we wait for collecting data. If I move the cursor, I can select this and we wait for responding. When the data are collected, you have to know that the movement is more accurate and with a normal speed. Look here. The bouncing of the balls till the second 0.5, and then the rotation begins. Look at the trajectory of the mid point, the center of the ball. and also look here. Now the bouncing of the sabots will begin. Poke! Yes, this is the contact and this is the slowing. Contact, slowing speed. This is the speed. Yes, this is the time. Horizontal and vertical is the speed. The speed is here in millimeters per second. Here is the time and here is the speed. You see? Now we don't have times to wait something or to construct. Everything is known by Inventor. When you start the dynamic simulation after you download the assembly, you will have to wait only this change if you want to change from 5 seconds to 2.5 seconds. But it's at your will. Good. Let's see what are the details. What is the imposed motion and so on. I have to go to construction mode now. Even now the data are collected. If I don't change anything here or in the joints, the data remain unchanged. Okay, now let's discuss about the imposed motion and the friction. If you take a look here at the joints, you see a lot of them, standard joints, which comes from the constraints. Look here, if you select one of them, you see the constraint taken as a base for creating the joint. You see here a point. Yes, this revolution 19 has a point here. This means that it was changed something in this definition or properties. Let's see. Property of this very joint. We can select the degrees of freedom, which is only one. The position is 0.11 degrees at the start. The torque is enabled. You see, this is important, and we'll see what is the diagram. Here is the diagram of the imposed torque. Indeed, at the second 0.5, that imposed torque is increasing to 300 Newton millimeters. Yes, this is the value we apply to create the rotation. And you have to know that this is not imposed motion, but imposed torque. The difference is that when you work with imposed motion, nothing will change it. But when you work with joint torque, if other opposite torque is applied, it will make the change of the initial torque or total resultant torque. You see, this is the real way to study this special mechanism. I don't apply an immutable motion instead of an imposed torque. 0.5 is 0 Newton millimeter. At 0.8, this is 0.8 seconds, the value is 300 Newton millimeters. Good. We know now more about imposed loads. Okay. That would have been the imposed motion we were talking about, not torque. Okay. Now let's see which is the friction in every contact between drum and sabot. Right click, properties, and you see here friction of 0.2. This is the coefficient of friction which was placed there by us. We want to have a friction here, yes, to stop or to stabilize the speed, rotation speed. Okay, that's all. That's all the changes we made here. Of course, we applied the gravity because we want to have a natural behavior of this mechanism. Good. Now let's see what happens if I suppress the three contact joints between the sabots, the three sabots with the drum. Suppress joints, but I let this active because this is the contact between these two hubs. This is the mobile hub and this is the fixed hub with all of their parts. What I mean? I mean that when the rotational movement begins, the sabots no longer matter and they can be considered removed from the mechanism. And the only contact, the only limitation will be between these two objects. Yes? This is the force joint between them and this is the contact joint. Both are implied. Welded group 4 and welded group 11. You can look here. Welded group 4 is all this subassembly and welded group 11 is all that subassembly. Okay. Having this suppressed, let's see what happens. The movement starts with bouncing the balls because of the gravity force, and then look here, it will start rotation at the 0.5. It started. The rotation is increased, and now look here at the contact between sabots and drum. As you can see, the sabots goes through drum. Yes, they doesn't matter, sabots, but this matters. I'll take a look from the side and you see this is the new contact and the trajectory is a circle with the center of this axis. Yes, this is also interesting if you want to study such kind of mechanisms. Now I think you are all clear, my friends, on this dynamic simulation. Open this assembly, apply dynamic simulation, and try to repeat all my actions here. You will be satisfied. That's all for today. Thanks for watching. Bye bye.